Hello again, Year 13. Time to move into more of the A-level detail about the rate of reaction content. So, looking at the title there, the rate equation and orders. Now, this is nothing at all found in GCSE. None of this is covered at GCSE. This is very much the A-level development from GCSE. Bearing in mind, first of all, that all the rate of reaction experiments you do, anything you measure, any quantity you measure, and we did a thing about the quantities you can measure against time, are all actually proportional to the concentration of reactants. So therefore they do tell you a direct proportionality to the concentration. The rate equation, which is going to look like this here, is expressed in concentration. We need to understand what the components are. So, first thing, you cannot get a rate equation unless you do an experiment. Rate equations do not come from looking at the equation and going, oh, I think it'll be that. Now there is a little exception to that when you look at organic reactions, particularly substitution reactions, because they're all the same. But it's only based on the fact that somebody had done the experiment before and you look at your chemical and go, oh, it's a similar sort of chemical. But when you meet a new reaction to you and somebody says to you, let's work out what the rate equation is, it's going to have to be an experiment in order to determine it. So we need to know what these things are. Now R, I haven't got R written down here. R is the rate. We'll come back to the rate when we start doing things with this. So the rate constant, it's a small letter K, not a capital K, that's equilibrium constant. This is a rate constant. It is what it says. It is a fixed value for a particular reaction under particular conditions. So it's a small k. It has units. Come to that in a moment. Orders. These are the powers. So when you look at this rate equation here, there's the rate constant. That's the rate. The x, y and z, the powers up here, are the orders. Now in most reactions, you will find, firstly, the rate equation isn't that complicated. It's usually one or two chemicals. A, B and C would be replaced by the names of chemicals in a real experiment. You know, it could be hydrogen ions, it could be an organic halogenoalkane or something like that. And there often are only one or two. I've done here for three, just to give you the general picture. So the powers, the X, Y and the Z, are called the orders. Usually you find the orders are 0, 1 or 2 in A-level questions. That's because of the nature of the types of questions that you're going to get. It is sometimes bigger, but not very often. Concentration is just that expression of the chemical in square brackets. Now the units of rate, always the same. The units of rate has to be moles per cubic decimeter per second, because it is the rate of change of concentration of a reactant. These will be reactants, or at the very least a chemical involved in the reaction, even if you can't see it in the equation. That's because it's a catalyst. Units of K. K has units every single time, but the units of K depends on the construction of the rate equation. So the rate equation may well be just two chemicals, and they might have the numbers 1 and 1 up here, X and Y, 1 and 1, which means you wouldn't write them in in the usual way with chemistry, we don't write a 1. That would give you some units for rate constant. If it was just a single chemical with a 1 and B and C weren't there, then it would have different units. So you have to be able to derive the units for the rate constant. We'll do a bit of that as we get further into our video today. So just to recap so that you're talking about the right things, here's the language. I was going to write vary down there, like that. So just to recap, R is the rate, K is the rate constant, concentrations of chemicals, and you do get questions in A level where there are non-specific chemicals, A, B and C, and orders of reaction are powers, and you can hear my pips going off, so that's time telling me it's time to stop. I'll see you after I've cleaned the board. Okay, so let's do an example. A non-specific example, A, B and C. Now, worth noting down things as we go along. That rate equation there is going to be the rate equation for this example. You need that. I'm going to talk about individual orders, overall order, and how to work out the units of K. We'll go through all of that in just a minute, don't focus on that. Let's just think about this because you need to note this down. So when you talk about individual orders, I've written OWRT. Any ideas? Order with respect to. It represents in note form. So you would have the following statements. The order with respect to A is 2. Writing time. The order with respect to A is 2. If you need to pause the video to write that down, please do. Then, the order with respect to B is 0. And the order with respect to C is 1. Now there's nothing written there because chemistry doesn't write ones, but I'll just put it in for you. You caught up? Order with respect to. So it is the order with respect to a chemical is the power. Overall order for that is all the orders summed up 3. Now I did say to you most examples are not as, they're usually 1 or 2. It's merely because I just wanted to make all the points. Because it's quite a complicated A-level question perhaps if it was that. But you do get them. Now let's talk about the units of K. Now, I said to you just now the units of K vary depending on the rate equation. So this rate equation will have the rate equation units for a third order overall reaction. They're not the same for second or first. There is a pattern to it if you wish to do that. So that's the rate equation. R equals K, A to the power of 2, C to the power of 1. I don't need to write B. If you're not mathematically minded, you'll have no idea why, perhaps. But anything to the power of 0, no matter what it is as a number, and these will be numbers, let's not forget that concentrations are numbers, they're moles per cubic decimetre as a number. Any number to the power of 0 is 1. So multiplying anything by 1 doesn't do anything, so we just ignore it. So anything to the power of 0, anything that is 0 order does not appear in the rate equation. Now that has consequences for what we do later on in this topic. So there's the simplified rate equation from this one. I have written it out as, and this is my way of getting it across to you how you do it. Square brackets represents concentration. Concentration is moles per cubic decimetre, but we'll do that bit at the end. So it's concentration per second, that's rate, that's the R, that's the units of R. K is what we're trying to find out the units for, so we don't know what they are. A to the power of 2, concentration squared, and that is concentration there. So that is the equivalent of concentration to the power of 3, but I'm not going to do it like that. I'm just going to then bring those down the bottom of there in a sort of get everything on one side and leave the k on its own mathematical thing, then those will cancel out because there's a square bracket on the top and a square bracket on the bottom. You could have put them together to be 3 and cancelled out one of them and ended up with 2. So k is seconds to the minus 1 over concentration squared. What does that come out as? Well, concentration squared is the square of concentration at moles per cubic decimetre, which is moles squared dm to the minus 6. So it is, that's a pretty shoddy k, but there we go, seconds to the minus 1, and then we'll put in the actual units now. So that's the concentration units, moles per cubic decimetre squared, but they're on the bottom of that expression. So the units become dm to the 6 moles to the minus 2 seconds to the minus 1, because the second is still on the top. So you bring them dm to the minus 6 up to the top, you flip its sign, from minus 6 becomes plus 6, 2 becomes minus 2. And I write them the other way round because the minus signs mean per, and it doesn't make sense if you have moles to the minus 2 dm to the 6. I mean, technically it's not wrong, but speaking it makes no sense. Per mole squared decimetre to the 6 makes no sense. It's decimetre to the 6 per mole squared. Grammatically makes more sense. So that's working out the units of a rate constant. I said there's a pattern to it. This is the third order version. So these are up the overall, and it's that. If you go second, it's that, and if it's first, then you're taking out a moles per cubic decimetre inverted unit, so dm to the 3 moles to the minus 1 each time as you come down from third to second to first. So you have two choices. You can work them out like that, because that's where they come from, or you can just remember the pattern. I don't know which is the best for your brain. You'll probably know that. Now I'm going to do a second example, but I need to get the board ready, so I'll see you in a moment. Okay, so here's the second and final example of what's going on in this video. The equation is again not a proper equation for the rate equation with real chemicals. Didn't want to get involved in all the palaver of writing out chemical names. So the rate equation this time, different letters, different orders. Do you know what that is overall as an order? Yeah, you do. It's 2. It's a second order overall reaction. First order with respect to G, first order with respect to H, and therefore second order overall. Now this slightly different sort of question, going to calculate the value of K, which if you've looked down the board is already there. You don't want to see me write on the board, so it requires some information. It requires what is the value of the rate, and I picked a value there of 0.0322 moles per cubic decimetre per second, and a concentration of G and H when this rate occurred. So at these concentrations, that was the rate. Now this could be like an initial setup, so you set these two up to be these concentrations in the container, and when you put the second chemical in and the reaction got going, that was the speed it got going at the beginning. It's called an initial rate. We had that off the graph before. So we're going to calculate, it says here, calculate the value of K and include the units of K. So it's simply a mathematical thing. The rate is 0.0322, K, that's what we're trying to find out, 0.5 and 0.125, both the 3 significant figures. That's 3 significant figures, so our answer must be 3 significant figures, because nothing can be more accurate than your data was at the beginning. So you rearrange that. K, so you put the 0.5 down the bottom, 0.125 down the bottom. I've just written the K instead of on the right, on the left. And it's 0.0322 divided by those two numbers multiplied together. And when you work that out, it comes out as 0.5152. But that's 4 significant figures. That's one too many. It's 0.515 to 3 significant figures. Here it is to 3 significant figures. What units does it have? Because all rate constants have units. There are none that don't have units. So here's the simple shuffle around the square bracket thing. Concentration per second is the rate constant times 2 lots of concentration there multiplied together. Pop those underneath. That leaves the K on its own. What do? We cancel that out, cancel that out. It's 1 over concentration per second. So that is dm3 moles to the minus 1 seconds to the minus 1. Here's the actual answer in the correct number of significant figures with the units as requested here in the what I want you to do. Now I just want to say one thing about why we do this. The rate equation and the orders are really important in terms of understanding the inner workings of a reaction. So when you've had mechanisms, now there's usually up to this point mechanisms have applied to organic reactions of one kind or another. Those reactions have a mechanism. That mechanism was proved and established by finding the rate equation. Now there's a really important thing that you would look at from the rate equation. It's called finding the rate determining step, and it is part of the mechanism. But that's another video entirely and not for today. The next video we're going to do is also not going to be about rate determining step. It's going to be about graphs. So I'll see you for a video about graphs. Thank you for watching, and I'll see you soon. Goodbye.